Now we move to a very important part of Markov chain, namely what is called the decomposition of state space. Now, recall that Markov chain typically corresponds to an evolution of a system over time, and the time is discrete here. So, for example, random walk. It starts from a point and then move to one of the neighbors, and then goes to another neighbor, and so on. This is an evolution of a system. Okay, there are other examples as well. So there can be queuing systems, or there can be other systems. It can also systems arising in physics or biology. They can always be modeled with using Markov chains. But the point is, it's an evolution of a system. Now, in order to understand this evolution, it's very critical to understand what paths through the path space of this, what paths through the state space are allowed. Okay, so what are the paths that are allowed? So if you start at a particular point, what are the points you can visit, and so on. This will help us understand the allowable movements of the process or of the system. Okay, so this is what we are going to do via a very canonical decomposition of the state space. Okay, so we'll not. I won't be able to give you the decomposition right away, but we'll move towards that. That's how I'll put it. And note that the whole thing that we have in mind is to understand how the evolution takes place. This decomposition is the sole purpose of this decomposition is to understand the evolution better. Okay, so we start with what is called a heating time. So you take a subset of the state space, let's call it B. The heating time of B is defined as, is denoted by tau B, is defined as the first time the Markov chain hits the set B. So this is the infimum for n bigger than or equal to 0, xn belongs to B. Okay. Now note that whenever we take an infimum, in order for that to be well defined, the set in question should be non-empty and it should have a lower bound. In this case, the lower bound is trivial because infimum is taken over all non-negative integers. So 0 is a trivial lower bound here. But the non-emptiness is not at all obvious. It can actually so happen that the Markov chain may miss a set B. Okay. So therefore, we'll make it, whenever that happens, we'll make it infinity. In the sense that we'll use the convention that infimum of an empty set is infinity. So that will give us, whenever the Markov chain never hits B, we'll just make this infinity. Okay. Now we'll be abusing the notation and write tau j instead of tau singleton j, okay, for every state j. So in other words, for every state j, tau j will denote the heating time of j. And again, it can be infinity if j is never hit. Now here is the definition. For two states I and j, we say that state I leads to the state j if, starting from I, there is a positive probability that after finitely many steps, we'll hit j. So in other words, see, pi will always, as we decided, pi denotes the probability of the Markov chain when the Markov chain starts at I. So if the Markov chain starts at I, tau j is finite with positive probability. So there is a positive probability that it's possible to hit j starting from I. So this is exactly what I have written here. In other words, we say I leads to j if starting from I with positive probability the Markov chain hits j. And this is precisely what is written mathematically. Okay, so just to be clear with the notation, tau j is the infimum of all n bigger than equal to 0 such that xn equals j. This is the heating time of the state j. It's also called the first heating time of the state j. We'll talk about it later, but at this point, let's just call it heating time. And again, here also we're using the convention that if j is never hit at all, we're just going to define this as infinity. So we defined I leads to j whenever this happens. So starting from I with positive probability, the Markov chain hits j. If that happens, we will say I leads to j. Now the notation we'll use is I leads to j. It's a very standard notation. By the way, this part that I'm covering is just from The Adventures in Stochastic Processes written by Sidney Resnick. So if you have not already done it, please download the book from a standard page, LibChain or somewhere. Okay, it's available. It's available in all the standard places. Now there are, I'm using the book of Sid Resnick, and he actually he doesn't use I leads to j. He uses the term j is accessible from I. But I'm going to just say I leads to j. I'm always going to write this. This is also Sidney Resnick's notation. And I'll just say I leads to j. Okay? But there are various synonyms. Instead of I leads to j, you can say, as Sidney Resnick says, j is accessible from I. Or you can just say j is a confluent of I. It's a very fancy way of saying the same thing. Or you can say j can be reached from I. Okay, so there are various terminologies that can be used. I'll just use I leads to j in this lecture. Now, before we move on, I would like to make a very easy observation here. Note that in the definition of the heating time, I'm taking the infimum over n bigger than or equal to 0. So in other words, if I put j equal to I in this definition, if you start from I, see if x0 is I, then of course, tau I is equal to 1, is equal to 0, sorry, because this is the infimum over n bigger than or equal to 0. So if you start from I and j is I, then you are going to hit at the 0th time point, and therefore this tau j would be 0, and in particular, tau I would be 0 starting from I, and therefore, in particular, tau I is finite with probability 1, in fact, not just positive probability. Okay? So therefore, what this says is that for every state I leads to I. Okay? So this is because of this infimum having n bigger than or equal to 0. And therefore, starting from I, tau I is finite with positive probability. Starting from I, tau I is actually equal to 0 with probability 1. And therefore, in particular, this holds. So I always leads to I.